Hi, and welcome back to our AP Chemistry Flipped Classroom. Today we're talking about rates of reaction and rate laws. And these two things are very closely related. And so we're going to learn how to distinguish between a reaction rate and a differential rate law and an integrated rate law. We're going to be able to discuss those factors that increase or decrease the rate of reaction. We're going to be able to use stoichiometry to determine the rate in terms of each of the reactants and products. You're going to learn how to determine a differential rate law from initial rates data and how to use that rate law to determine the effect of changing the concentration of any of the reactants on the rate of the reaction. So let's jump right in and talk about what a rate of reaction is, or what a reaction rate is. And so reaction rate is analogous to the speed of a reaction. So just like we measure the speed of our cars in the change in displacement over time, we measure the rate of a reaction in the change of concentration of a reactant over time. And so we can think of rate as being the change in concentration. So the concentration at a time 2 minus the concentration at time 1 divided by the difference in those two times, or the time elapsed. And so we can write this as the rate is equal to the change in concentration of the species we're interested in over the change in time. And that's a rate of reaction. So obviously, like everything else in chemistry, molar ratios play a role here. So we're going to talk about how we express reaction rates and how we can use stoichiometry once we have those reaction rates. So remember, reaction rate is just the change in concentration of a reactant or a product per unit of time. So we can measure reaction rates. We can monitor the change in concentration of either reactants or products as a function of time. And so we really can talk about rate in three different ways. We can talk about initial rate. So this is the rate right as the reaction begins. And sometimes you'll see this referred to as instantaneous initial rate. We can look at average rate. So that would be the change over a longer period of time. And we can look at instantaneous rate at any point in a reaction. So let's look at an example of a reaction, and let's look at those three rates. So we have this reaction, and we have butyl chloride is one of our reactants. It's reacting with water to form butanol and hydrochloric acid. So we're measuring the concentration of the butyl chloride at various times. And so if we want to find average rate of reaction, we can find an average rate of reaction for the whole reaction, or we can find it for each time interval. So for each time interval, we would find the change in concentration and divide it by the change in time. Okay, and so you can see that we have these average rates. We would look at the change in concentration over the change in time to find each of these average rates. And you'll notice that as the reaction proceeds, this average rate decreases. And that makes sense because as our concentration decreases, we're going to have fewer effective collisions, which means we're going to have a slower reaction. Fewer collisions means fewer reactions. Okay, the second type of rate that we can talk about is an instantaneous rate. So if we were to plot the change in concentration, or plot the concentration of the butyl chloride over time, then we could draw a line tangent to that curve at any point, and that would give us the instantaneous rate at that time. Notice that at the beginning, our reaction is faster. We have a higher instantaneous rate, and towards the end, we have a lower instantaneous rate. So the best indicator of the rate of reaction is that instantaneous rate at the beginning of the reaction. So where does stoichiometry come in here? So in this reaction, our ratio of butyl chloride to butanol is 1:1. So the rate of disappearance of butyl chloride is the same as the rate of appearance of the butanol. But what if the ratio is not 1:1? So in this reaction, we have our hydrogen monoiodide reacting to give us hydrogen and iodine. So in this case, our rate is going to be the change of the hydrogen iodide concentration divided by the change in time. But because we have twice as much hydrogen monoiodide as we have iodine, the rate of the reaction would be 1/2 the change in hydrogen monoiodide concentration over change in time, or the rate of appearance of the iodine over time. And so this is just that stoichiometric coefficient. For every 2 hydrogen monoiodides, we have 1 iodine. And we have a negative sign here because the change in concentration of hydrogen monoiodide is going to be negative. It's going to be decreasing. The change in concentration of iodine is going to be positive because it's going to be increasing. So for any reaction, our rate is going to be 1 over the coefficient times the change in concentration over the change in time. And so this is the rate, as we like to say, per mole of reaction. So this is just as if everything had a coefficient of 1. Okay, so we can look at it from this perspective, or we can look at this graphically. And what we see here is the concentration over time of these 3 species in this reaction, where we have nitrogen dioxide decomposing into nitrogen monoxide and oxygen. And so you can see that the concentration of the nitrogen dioxide is decreasing, and the concentration of the nitrogen monoxide is increasing, and the concentration of oxygen is increasing as well. But the concentration of oxygen is increasing at 1/2 the rate that the concentration of nitrogen monoxide is, or that the concentration of nitrogen dioxide is decreasing. And that's because of those stoichiometric coefficients, or those mole ratios. So we can measure the disappearance of the reactants, we can measure the appearance of the products, and it's always going to be proportional stoichiometrically. They're also always going to be equal to the slope tangent to a point. That's going to give us an instantaneous reaction rate. Okay. So what are some of the things that cause a reaction to go faster or slower? So if we go back to this idea of effective collisions. So in order for a reaction to happen, we have to have it has to have sufficient energy, it has to have the correct orientation, and we have to have collisions. So as the energy increases, as temperature increases, we're going to have more collisions. As we have more collisions, more of them are going to be effective. We are also going to have more of them that have sufficient energy to overcome the activation energy. So more collisions, more higher energy collisions is going to equal more effective collisions, is going to equal a faster rate. The other piece that is going to affect our reaction rate is concentration, because if we have a higher concentration, then we're going to have more collisions because we have more molecules. And so that's also going to increase the number of effective collisions. And then finally, we can talk about a catalyst. So if we have a catalyst, that's going to lower activation energy. So that's going to mean that more of our collisions are going to have sufficient energy to overcome that activation energy. And so we're going to have more effective collisions, which means we're going to have a higher reaction rate. So what do we know about reaction rates? We know that they are stoichiometrically related. We know that we can measure them by instantaneous rate, by average rate, or by initial rate. We know that increasing concentration, increasing surface area, and increasing temperature will all increase reaction rate. And that those opposites will all slow down the reaction rate. So now that we've addressed reaction rates, let's talk about rate laws. So we have two different kinds of rate laws that we talk about. We have differential rate laws and we have integrated rate laws. So today we're going to address differential rate laws, but I do want to just talk about both of them briefly. So differential rate laws express the relationship between concentration of reactants and rate of reaction. So this is a relationship between concentration and rate. And this is the one we usually just call a rate law. An integrated rate law expresses the relationship between the concentration of reactants and time. Okay, so there are two different rate laws. They give us the same information, but they give it to us in very different formats. And we arrive at them from very different sets of information. So if we're given information about concentration and rate, then we know we're looking for a differential rate law. If we're given information about concentration versus time, then we know we're looking at an integrated rate law. So let's talk about these differential rate laws. In order to write a differential rate law, what we are usually given is information called initial rate data. And so what we've done here, or what someone has done here for us, is that they've run this experiment 4 different times, and each time they've used different concentrations of the reactants. And they've measured that instantaneous initial rate. And so from this data, we're going to be able to figure out what the relationship is of the concentration of each of the reactants to the rate law. And so you'll notice in our data here that we have concentration information for each of our reactants, and then we have rate information for each of our trials. And so you can see that in trial 1 and trial 2, we have kept the concentration of the chlorine constant, but we have changed the concentration of the nitrogen monoxide. And if we look at trial 1 and trial 3, we can see that the concentration of nitrogen monoxide has stayed the same, but the concentration of chlorine has changed. And so that's what we're going to use in order to determine this differential rate law. So when we write a rate law, our rate law is going to be R, or rate, equals K, which is a constant, which will be unique to each reaction, times the concentration of the reactant raised to some power, we call that an order, times the concentration of the other reactant also raised to some power. And again, we call that an order. And so what we need to do in order to write the rate law is figure out what these powers are, this X and this Y, and what's the value of K. So as I said, in experiment 1 and 2, the concentration of chlorine is constant while the concentration of nitrogen monoxide doubles. At the same time, so this doubles from 0.25 to 0.5. At the same time, this number, our rate, quadruples. This rate, 5.72 times 10 to the negative 6th, is 4 times the concentration here. So we want to know when we raise chlorine, when we double chlorine, what is this exponent if this R quadruples? So what we're really asking is 2 to what power is 4? And so we all know that 2 raised to the second power is 4. And so our reaction is second order with respect to our nitrogen monoxide. So now we know that there's a 2 there in nitrogen monoxide. That's second order with respect to nitrogen monoxide. Now we want to repeat the process to figure out the order with respect to chlorine. So now we're looking for the time when the nitrogen monoxide concentration is constant, so 0.5 and 0.5, and the chlorine concentration is changing. So we've gone from 0.25 to 0.5, so this has doubled. At the same time, the rate also doubles, so our reaction is first order with respect to chlorine, because 2 to the first power is 2. So we've now figured out that it's second order with respect to nitrogen monoxide and first order with respect to chlorine. So now we pick any one of the lines, it doesn't matter which one, we've chosen experiment 1, and we just plug these two values for nitrogen monoxide and chlorine into this rate law that we've just determined. We have the rate, so we're going to go ahead and plug that in over here for R, and we're going to solve for K. And so we get a value for K that is 9.15 times 10 to the negative fifth liters squared per mole squared per second. The units of K vary depending on what these exponents are. Okay, and so you have to solve for them each time. So last step is determining the overall order of the reaction. And overall order of the reaction is just the sum of the orders for each of the reactants. And so since we have a 2 and a 1, our reaction is third order. Okay, as always, I hope this is helpful. If you have questions, I look forward to hearing them in class. Thanks. See you soon.